So I'm happy and I'm glad to hold this IMFTF keynote speech, which will be given by Professor Kristian Jessen from University of Southern California. Kristian graduated from the Technical University of Denmark in 2001. After that, he joined Stanford as postdoc and later working as research associate and acting assistant professor in 2006. And he joined the University of Southern California as assistant professor. And since then, he has worked in USC. Now he's a professor at the Department of Chemical Engineering and Materials Science in University of Southern California. His research interest is in fluid flow in porous media, especially multiphase flow involving complex phase equilibrium. So he worked on CO2 storage, oil and gas production, shale production, so many challenging multi-phase flow, multi-phase equilibrium problems. He has got many awards, and he's also holding the energy simulation chair founded by the CMG Foundation. Today, Kristian will give a talk about investigation of mass transfer and sorption in shale and variable net stress. So we look forward to Kristian's speech. Kristian, now the floor is yours.
Well, Wei, thank you very much for the introduction. So again, thank you very much for your kind introduction, and also for the organizers for inviting me to present at this event. As Wei mentioned, I'm going to talk about mass transfer and sorption in shales today, and feel free to ask any questions as we go along. I hope I'll be able to address them properly as we enter the discussion section at the end of the talk. Now, before I start on the topic of the day, I'll just give you a brief introduction to what I do. And Wei mentioned several of them. I'm very interested in unconventional gas resources and enhanced oil and gas recovery from also unconventional systems. And then I work also on modeling and simulation of gas storage. And I've worked quite a bit on CO2 storage in the subsurface. We're now transitioning to look also at hydrogen storage to see what we can do with the subsurface to facilitate a transition towards utilization of hydrogen in the energy portfolio. So within each of these categories, I like to combine experimental work with modeling and simulation to try to understand what's going on in these wonderfully complicated systems that we deal with in the subsurface. So the outline for today's talk is basically all related to shale, and I'll be happy to talk about other things, but it'll have to be after the meeting. But I'll start with an introduction about why I'm interested in shale and what the research objective and approach for the work I'm going to present is going to be, and I'm going to introduce also the shale materials that we're working with and take a look at some of the characteristics of those. Then the talk will focus a bit on the sorption behavior of various gases in shales, and here we'll look at both experiments and modeling of isotherms and sorption kinetics. And then in a separate set of experiments, we look at mass transfer shales, working with helium and using primarily helium expansion type experiments to try to understand how helium transport through this hierarchy of pore spaces that we find in shales. After that, we then turn to the combination of sorption and mass transfer, and how those two phenomena interact to define a new set of behaviors that we see when we work with gases such as argon, methane, or methane-ethane mixtures. And we're going to look at different scales. We're going to look at core scales and at smaller scale samples like cubes, back from larger samples. And once we're done with all that, I'm going to sum up and arrive at some conclusions, and then I'll be more than happy to take any questions that you may have. So now the role of natural gas from a US perspective is that, we've seen, if we look at the figure here, a substantial growth in the contribution of natural gas to the energy consumption in the US. And primarily what we see on this figure is that the natural gas production has been steadily increasing, and really started to kick off around 2006 when I joined USC. The natural gas production from the East Coast area, particularly the Marcellus, started to pick up substantially. And at the same time, it sort of replaced the need for coal over the same period of time between 2006 and 2020, where we are now, 2020s. And the replacement of the coal by use of natural gas has pretty much controlled the reduction in the emissions of CO2 from the US. So by just replacing coal with natural gas, they've done all the let's say reductions of the bulk of the reduction in emissions was really just by switching the fuel source rather than doing much of many other activities such as quenching. Really the feedstock that matters here. And what we see is we're sort of expecting this to grow in the future and reach, I would say, it's not 50%, but it's a substantial component of the energy portfolio in terms of consumption, while we wait for renewable energy sources to pick up and contribute more and more as we go. And if we ask where do we get the gas from, well, a majority of the gas that we produce is from tight shales, tight gas systems, or primarily shales that we find in various parts of the US, particularly on the eastern side of the country. Okay. So the expectation is that natural gas will continue to be a major player in how we generate energy for various applications over many years to come. Far beyond, I think my retirement is probably out somewhere here, and then we're still going to be going at it for a long time. And with that in mind, sort of seems an obvious thing to study, to try to understand what we're doing. We extract natural gas to become even better at it, since it's such an abundant resource that can help us serve many people around the world. Now, why did we become so good at producing shale gas? Well, the main contribution was really development of horizontal wells, multi-stage fractured horizontal wells. Here we just see a single well, but nowadays you have single pads with numerous wells going out in all directions to minimize the footprint at the surface. And we're drilling wells with 20 plus hydraulic stages on a regular basis. So it's really the engineering of long horizontal wells, stimulation technologies that have allowed us to access the resources in the subsurface. Because the gas that we're looking for exists either as free gas in the fracture networks that exist in the rocks, or the macropores that we also find, as well as to some extent the mesopores, and also as adsorbed gas in meso and micropores spaces in the subsurface. So the trick is basically to connect all of these, and therefore the petrophysical properties of interest to us are really simple. It's the usual porosity, permeability, and also to some extent the composition of the materials that we have, because it just controls the amount of adsorption that we often find. But underneath these two simple terms, porosity and permeabilities, we sort of have this hierarchy of scales that we have to worry about, and how they're connected to allow gas to transport from shale to the larger fractures and then eventually into the wellbores to be And we need to be able to describe or both measure and model at all these different length scales that are playing central roles here. Now, just a simple picture to sort of set the stage for how the challenge really is, even at the laboratory scale. And here's just an SEM image of a shale sample, and you can see the resolution here is in the 30th of micron range. And if we zoom in and take a little look at a little hole over here, we see that it's not a very nice and homogeneous material, and we have inclusions of all kinds, including small features that we see either here or here, that if we zoom in further from a resolution of 1 micron to hundreds of nanometers, we start seeing an abundance of small pores that could be attributed to kerogenic inclusions and other things. And these are all the scales that we need to map to or link together after we understand the individual contributions, and be able to describe to be successful in modeling and estimating production behaviors for these type of systems. So, objectives. Well, the things that we set out to do was to say, well, I work in a university, and in the university we have labs, so we go to the lab and we do measurements and try to make sense out of what happens at the field scale. So the question at lab scale we have to ask is that, well, I work with small samples, so can I take a little cube, a sugar cube of shale out here, and use that to predict what happens if I take a full diameter core where the diameter is 3.5 inch, right? Okay. And another question that we ask ourselves is that if we can use, surrogate gases such as helium and argon to try to characterize both sorption and mass transfer in these type of systems, and then use that to predict what happens for methane and ethane. Okay, because initially we were not very fond of working with methane as a flammable gas. We like to work with inerts, such as argon, which adsorbs just like methane does, but slightly less, as you can see over here. So basically, try to jump scales and work with different gases and translate the behavior we observe from one gas to another gas to sort of build this understanding of these materials and the mass transfer therein. And as we go through this, really what we're trying to understand is if we can learn from these type of studies and use variations in the produced gas composition. For instance, the ratio of methane and ethane as it's produced over time, to try to predict or interpret the performance of a well that has been drilled in subsurface. So today I'm going to primarily focus on this and try to link it towards the end to what one could potentially try to do with what we have learned from the lab scale to even larger scale. Now, so what did we do? Well, we were lucky enough to have access to 180 foot of core extracted vertically from the Marcellus shale plate in Pennsylvania, and so we had more shale samples that we could ever imagine to work with, because we can't handle 180 foot core in the lab. So what we did was we took out samples from specific depth of interest to us and did experiments with 1 cubic centimeter cubes and also a segment of the full diameter core that I'll discuss in more details later. Now, with these samples, we could study things such as sorption in terms of isotherms and kinetics. And we did that for cube samples for argon, methane, ethane, and mixtures of methane and ethane. And then we could study mass transfer also, either on the cube, try at least, or at the larger scale, and use things, techniques such as pressure decay or gas expansion experiments, or simulate production from a full diameter core, look at things, as reduced composition of time and so forth. That's what we did. So let's take a look at some of the samples that we have and what we work with. So here we have select depth along the 180 foot vertical section of the Marcellus plate that we were working with, and we got some data from standard characterization techniques such as the GRI technique, matrix permeability, which is based on ground samples, pulse decay type measurements. And as we can see, there's some outliers, but there's a general trend that as we go deeper, we actually have slightly higher permeability, slightly by a couple of orders of magnitude. But in general, the matrix permeability is very low. So here we have a micro Darcy, here we have a nano Darcy, and so forth. So things are not very permeable in the matrix segments of this shale. And from helium pycnometry, we can get the porosity also for the same samples at similar depths as over here, and we see around 6% porosity is sort of an average, and there's a slight trend of increasing porosity as we go deeper in formation. Now, if we look at things such as mineralogy clay versus total organic content, we see higher clay typically at the top and more organic content at the deeper sections. Here we just show clay versus TOC. And if we plot things such as permeability and TOC on a log-log scale, well, there's a sort of a clear trend that the more organic content, the higher the permeability we have. But we have to remember, whenever we plot on a log-log scale, everything seems to follow some trend. It doesn't necessarily mean anything because we really compress the data. If you just look at a vertical segment here, we're scaling, jumping like 3 orders of magnitude in permeability, although it still seems that there's a general trend. Let's be a little careful with that. Now, in terms of the gas content, the total gas content was estimated based on desorption characteristics and estimation of lost gas. And here we just see let's say the recombined amount of gas that is measured plus estimated, and we see that as we go deeper in formation, we have more gas, and that is also consistent with the organic content that we have that increases as we go deeper in formation. The surface area here in meters squared per gram is also measured, and we see as we go deeper, higher organic content gives us higher surface area, and it also rhymes with more gas in place. So deeper is better in terms of getting access to the gas or the volume of gas that can potentially be extracted. An interesting observation is if we plot the estimated lost gas as a function of depth, we see that the estimate of the lost gas is fairly high. It's about, average is around 60%. And we use that lost gas estimate to piece together our total gas that we use in terms of the economics of estimating what can potentially be achieved from the production here. And we see that there's a nice trend between total gas and lost gas, and the conclusion is the lost gas that we're estimating is quite substantial. So we have to be a little careful with how we estimate the lost gas by extrapolating back from desorption behavior that we observe when we take samples to the surface. Now, let's take a look at helium and argon behavior. So if I want to go to the lab and I want to measure adsorption, you can use volumetric methods or gravimetric methods. We primarily work with gravimetric methods and use magnetic suspension balance to study adsorption behaviors of porous structures. And what we do in the lab is that we measure an apparent weight of a sample subject to some buoyancy, and the apparent mass includes sample container, and any mass of acid that we have stuck onto the sample. And from that, we have to subtract the buoyancy that acts on the volume of the sample container, and the volume of the acid phase as well. Now, if we rearrange this first equation into what we know and what we don't know, we can calibrate the mass of the sample container, and the buoyancy effect of those from calibration with helium expansion experiments, assuming that helium does not adsorb onto the surfaces of this material. And everything else is the true mass of the acid phase minus the buoyancy acting on that volume of the acid phase, which is the excess adsorption that we can measure. So we don't measure absolute adsorption, we always measure excess adsorption. And then we have to somehow convert this back to absolute adsorption to do estimates of gas in place, to simulate production behaviors and other activities. So here we just have a picture of the calibration exercise you do for a given sample. You get the apparent weight as a function of gas density. And we see a nice straight line, which is consistent with the fact that, you know, the gas density acts on the skeleton and the sample volumes to reduce the apparent mass that we observe. And from that, we can estimate the skeleton volume and the container volume. And if you do a separate measurement with an empty container, then you can figure out what your actual skeleton volume is. So, and then once you have that, and you switch to an adsorbing gas here, you see argon. We have the excess adsorption as a function of pressure. This is two different measurements. They agree fairly well, so we have good reproducibility here. Now, this is just the isotherm. We can also, as we transition in pressure and wait for things to equilibrate, we can learn something about the sorption kinetics. It's a little more tricky, but I'll show some of that for argon in one of the following slides. So we have two things here. We can look at the isotherm, the equilibrium behavior, and the sorption kinetics. Now, as I mentioned, we use the suspension balance, and the accuracy here of that is about 10 micrograms, which is fairly accurate. We work with the cube shown here, which is roughly 1 centimeter cube. And we chose originally to work with argon because it has a sorption behavior that's similar to that of methane. Only that argon is not going to catch fire, and we have to train students to work safely first for that, and then we switch to methane later. And over here, we observed the excess adsorption that we observed for argon. And we took a first swing at modeling this by just using the simple Langley isotherm, given the behavior that we observed. And to do that, we know that we can calculate absolute adsorption from Langley's isotherm through a maximum sorption capacity and a fractional coverage, which is related to the sorption constant and the pressure in the bottom. Okay. Now, since we are measuring excess, we need to convert absolute to excess to be able to estimate the max sorption capacity and the equilibrium constant. And we do that by scaling or rescaling the excess with respect to differences in bulk phase and adsorbate phase density. The only problem is that we don't really know what the adsorbate phase density is. And we often make assumptions such as, oh, it can be the density of saturated liquid at the normal boiling point, or it could be some function of a maximum density in close packing, and that of the critical fluid in bulk times fractional coverage. This is an approach referred to as the lattice density functional theory model. If we do that, we can basically estimate the parameters for this, the maximum sorption capacity and the equilibrium constant, by matching our excess data with the Langley isotherm substituting here and an assumption about the adsorbate phase. This is all good because I like the agreement. I think it's a pretty good agreement here. However, if I change my density model around and say, well, I could have different assumptions about what I believe the adsorbate phase density is, what I find is that I can still match my data. I can have a constant value, which is the maximum closed pack density of argon that I can calculate separately. I can take the critical density of argon and keep it as a constant, still match the data. The bottom line is that you end up with a range of equilibrium constants for the isotherm, and also a range of sorption capacities, which goes here. It's almost a factor of 2 between low and high. Now, why should I care about that? Well, if I want to estimate gas in place, I need to know the absolute adsorption. Okay? And there's literature discussing how to calculate gas in place, including sorption, and doing the proper job of that, where we calculate both the free gas contribution and the adsorbed amount in an absolute sense. So there are two terms. Well, there's one term here that tells us the gas in place, which is here in standard cubic feet per ton, and includes a term here which is the adsorbed amount that we need to calculate separately based on knowledge of the total or the absolute adsorption that we have. Now, if I use these different density models, I get a different isotherm in terms of the absolute, although they all agree on what the excess absorption is, like I showed you on the previous slide. They all agree here on the data. But then when I calculate the absolute absorption, I see a good spread here, particularly at higher pressure. And when it comes to estimation of original gas in place, here in SCF per ton, we see a good variation in terms of the outcome, depending on how I choose to describe the aspect phase. So we have to be a little bit careful there, and there's a lot of good work that still needs to be done for us to better understand what is the aspect phase density as we model these type of systems. Now, as I mentioned, we measure the excess absorption by gradually ramping up pressure, waiting for equilibrium to be established, and then move on. In between these equilibrium stages, here you see that the excess absorption gradually changes with time, which reflects one of two things. Okay? It can either be the mass transfer that's going on, that takes time for things to transport into the cube and sorb and reach equilibrium, or it can be the kinetics of absorption that you observe. If you look at the size of the sample that we have, it's easy to convince yourself that mass transfer in this sample is very fast. The characteristic length is 0.5 centimeter, and even if you have a fairly low diffusivity, it wouldn't take long to get mass transfer into the system. So we prescribe this transient that we observe being due to a net absorption rate of gas onto the surfaces. Okay? And that can be described also by a Langmuir type model where the change in adsorbed mole numbers with time is a balance between adsorption that we represent here and desorption that you see here. Ka is, if you remember, is the ratio of the kinetic constant for adsorption divided by that for desorption. So in this figure I show you here, I have fitted the data to the kinetic model, and I've done it in two approaches. So in the first approach, I said, well, I did measure the isotherm already separately. So Ka and the max amount of adsorption, I can take from the isotherm, and then I have one parameter to estimate, which is pKa, which is the specific surface area of the material and the kinetic constant, let's say rate of adsorption. Okay. Now, if I do that, I get a decent agreement. However, if I choose a second approach and say, well, I need to realize that I'm not particularly certain about my aspect phase density model. So what if I match all three parameters at the same time? Because the change that we observe here is in part due to the buoyancy acting on the aspect phase, and we're assuming a density model, meaning that we're assuming an aspect phase volume implicitly. So if we go that route instead, we get a far better agreement between the data and the observed data and the calculated results. And that basically tells us that, well, we have to be really careful here. Although it's convenient to measure and try to model an isotherm separately from the dynamics of a process like this, we may not get the best result because some of the assumptions that we make are embedded in our parameters that we estimate. So now, if we now go on to talk a little bit about measurements or experimentation with the full diameter core, we have pictures shown here. This is the actual core. The core was slabbed. This is a 3.5-inch diameter. It was slabbed 1 inch from the circumference, and we had to make an epoxy insert to complete the cylindrical shape so we could fit it in our core holder and into our experimental setup. So effectively, the core that we're working with look like this, where we have our epoxy. We have a macro fracture, if you will, that cuts the bedding plane. So you can think of it as a vertical fracture in the subsurface, okay, that connects all the layers that we expect having in our shale deposit. This particular core was 7 inches long, shy of 20 centimeters in length, and 3.5-inch diameter. So the volume of shale that we're looking at here is It's about 1,000 times more than what we use for our sorption experiment. The magnetic suspension balance. Now, down here we have a little schematic of the setup. We have an upstream section, we have the core holder sitting here, and a downstream section. And what we do is we have a reference volume upstream that we can charge with gas while the core and the downstream segment is evacuated. And then we can expand the gas into it and observe pressure variation as a function of time. We can do this with different gases, and we start with helium, assuming that it's not absorbing, to try to characterize the mass transfer behavior in this system. And the way we think of it is that, well, I have an upstream volume, that a reservoir that I can charge, expand through whatever fracture that I have in my system. Here, that would be primarily the microfracture. Then the microfracture will communicate with the matrix, and the matrix is envisioned to be made up by different segments, mesoporous. We talk about a mesoporous range and a microporous range. So mesoporous is supposed to include everything greater between 50 nanometer down to 2 nanometer, and microporous up below 2 nanometers. Now, we can do first helium, that where we don't expect any absorption impact, and then we can do it again with argon and see how transport and absorption interact. So let's start with the helium. So if we do a helium expansion experiment here, we start with around 50 C. The initial pressure was about 64 bar, and the gas expands into the system and stabilizes at around 58. Okay. We can then estimate based on that what is the pore volume to helium that we observe. And the pore volume in the sample was about 44 cc. A similar experiment was then done with argon, and you see argon arrives at a much lower pressure because of adsorption phenomena that steals gas from the bulk phase onto the surfaces. And if we were just to ignore that and interpret the pore volume based on the pressure, we would have an effective pore volume of more than 100 cc, more than twice of that we would probe by using helium. Now, so if we look at a helium expansion experiment here, we see originally the pressure declines somewhat rapidly here and transitions into what we refer to as a mesoporous range, and then finally we have mass transport in the smallest of the pores. From the helium expansion experiment itself and knowledge of dead volumes associated with the experimental setup, we estimated a porosity here around 5% of the sample that we were putting. So it's slightly shy of the porosity values that were observed for all the different depth, which was around 7%, but it's still within reasonable range. Now, so to model this type of system, we set up a triple porosity model based on this idea that there's a main fracture that we actually engineer ourselves by using this epoxy insert, and that gas that flows into that fracture can communicate with the matrix in this way. So we have this hierarchy of pore spaces. We can write a material balance for the fracture, where we assume that the fracture volume is constant, and we have the accumulation term, the flux term, which is just Darcy flow in the fracture. And then we have an exchange term where the fracture talks to the matrix, to the mesoporous segment of the matrix. Okay. Now, if we go to the matrix segment now, we can write a conservation equation for gas in the system as well. We have the accumulation term of free gas. We have an absorption term now that is not in use when we're dealing with helium, but very much active when we're dealing with argon. And then we have this exchange term between fracture and matrix. And now the mesoporous range, which is denoted M, can talk to the microporous range denoted mu. And finally, we have an equation for the microporous space. The transport between domains are explained through transfer functions, where we have a shape factor and effective diffusivity, a driving force in terms of gas concentration, and then a factor beta, which is only a function of initial and current compositions. It's a special share. It's a correction factor that captures the transient in very tight systems. I won't have much time to talk about that today, but it's something that was developed by Vermeulen back in the 60s for studying diffusive mass transfer in ion exchange columns, and it works beautifully well for very low permeability systems. The interesting portion here is the product of sigma and d, which is equal to the inverse of the characteristic time for transport. So for us to get volts per cc per second, this has to be 1/2 seconds. So it gives us a peek at how fast the transport into a segment, a certain segment, will occur. Okay. Now, when we talk about the sorbing species such as argon, methane, methane, we describe the absorption terms in the mesopores and micropores through a through, let's say, Langer's kinetic model, where we have weight of the core, specific surface area associated with the mesopores, absorption rate constant, and then there's a driving force for absorption and a driving force for desorption. Same for the micropores. We assume that the absorption constants or kinetic constants are the same for both micro and mesopores, which is, debatable, but we can talk about that later. So that leaves us overall. Oh, there. Okay. So that leaves us with 4 different parameters that we need to estimate to use this model. The first one is the fracture permeability. Then we have two inverse characteristic times, one for mass transfer into the mesopores, one for mass transfer into the micropores, and then the ratio of mesopores volume over the entire matrix pore volume. That's what we need to be able to So we first took a look at the fracture permeability, and we did that by doing steady-state flow-through experiments, just to try to understand what's going on, and also to try and understand what is the impact of net stress on the system as we go from high net stress to start with, when gas has been evacuated out of the system, to lower net stress when we let gas expand into the system. And we see that at lower net stress values, the permeability changes quite dramatically, while above a certain threshold, we start seeing a very flat behavior in the evolution of the permeability as a function of the net stress of the cell. So the experiments that we do, they go from, let's say, very high net stress to somewhere around here. So we're operating on the flat portion of the curve, which is helpful because then we have a good estimate of what the permeability of the fracture is. Now, the rest of the parameters we have to estimate from a helium expansion experiment. So we have an estimate of the fracture permeability, and then we have to estimate 3 parameters from the pulse decay or the pressure decay that we observe. And here we see the same experiment, but on different time scales. It's either log time or regular time. Okay. And we observe by estimating these parameters a very good agreement between the model and the experimental observations. And we see here that the inverse of the characteristic time for mass transfer in mesopores and micropores follow our understanding of what should be taking place. That the characteristic time for transport in the mesopores is smaller than that of the characteristic time in the micropores. In addition, we estimate that 80% of the matrix permeability resides in pores that are classified as being part of the mesopores range. So that's all good. So we have some parameters here now for the helium expansion experiment. And what we want to do is we want to try to combine that with some of the sorption observation we had for argon to try to see if we can predict the behavior of an argon experiment. Okay. But to do that, we need to look at the transport in the matrix, because as we switch from helium to argon, we need to rescale the model parameters. The characteristic times include information about an effective diffusivity and a shape factor. Okay. So the way we approach this was to say, well, we're sort of, typically in some sort of transitional flow where we can have contribution for viscous or Knudsen type diffusivity. There are other models out there that try to cover a broader range in terms of mean free path, etc. But here we use the simplified idea just to get a sense of what happened, and then we'll take a look. So if we write the flux approximately equal to the viscous plus Knudsen term and gradient in concentration, we can write it as an effective diffusivity that depends on pressure, both through pressure itself, but also pressure dependence on viscosity. And if we think of transport in a single pore, just for simplicity, we can write B and dk in terms of pore radius and molecular weight of the species that we have. So for instance, and we can figure out what is the characteristic time for transport. If I have a length squared divided by an effective diffusivity, I can estimate the time, but the time itself is really not the important part. It's the ratio between helium and argon that's important. Because if the characteristic time between transport of helium versus argon changes by a factor of 2, then we will have to rescale our model parameters accordingly, because we're working with the inverse of the characteristic time. So here we see the characteristic time for helium in a 1 cc cube, just for fun. The characteristic time is less than 10 seconds if your pore is roughly 6 nanometer in diameter, radius here. And that of argon is slower. So this tells us two things. It goes going back to the kinetics of adsorption, that things go really fast if you have a 1 cc cube, even though you have very small pores. And the magnetic suspension balance that we work with takes a sample point every 6 seconds. And what it tells us here, the characteristic time for the entire process is the same order of magnitude, meaning that we cannot really capture the transport in our magnetic suspension balance. We can only see the sorption kinetics, at least for samples that are of this size, or pores that are in this range. Okay. Now, bottom line is we can define a ratio of characteristic times, and for low pressure, we're about factor 3, and high pressure, we're about 2.3, and we sort of take an average value that sort of pertains to where we're operating the experiment, and we have some factor about 2.5. So what I can do is I can take the permeability itself from the main fracture. I can rescale my transport parameters based on this little scaling argument. And then I try to predict what happens with my argon experiment. And what we observe is that we achieve a very good agreement between the experiments and observation. It's not perfect, but given the fact that we have not actually estimated any parameters from an argon experiment where we expand argon into the system, we managed to get a fairly good agreement over the entire period of time that the experiment took place. Again, I showed here as log time or as real time. And we do see a few discrepancies here and there, but overall, the model does a great job with us estimating any parameters for the argon experiment itself. So that's the first portion of it. Now, if we talk about helium and methane, that was sort of the next step we took. We said, well, okay, fine. We studied helium and argon, and now we want to take it a step further, and we want to look not only at loading experiments, but also at unloading experiments. Most of the characterization work that is done with tight rocks is done with pulse decay type measurements rather than production experiments. So we wanted to try to see if we could do characterization with a pulse decay type measurement and predict the production behavior from subsequent experiments. And to do that, first we had to go through the hardship of measuring isotherms, which is a tedious exercise, but it has to be done. So we went and we measured on the same cube as before, the excess adsorption of methane, and we converted that to absolute depending on our adsorbate phase density. And we get a range of parameters, not as dramatic as for argon, but still some range. And just a reminder, we went back through the same exercise, main core, slab, the entire setup, and the interpretation. But now we modified the system on the downstream end, so we could measure flow rates of production and observe track the cumulative production over time. After we would load the gas in, and then we would simulate production afterwards. So Two types of experiments were done. The loading experiment A and B, see up here. Two experiments were done. Experiment A goes to slightly lower pressure than experiment B, and we sort of prescribe that to inadequate evacuation of gas between A and B experiments. So the student got a little lazy when it came to experiment B and didn't wait long enough to evacuate the core fully before starting the next pulse. And then two experiments were done. Depletion A, where the pressure on the downstream side was just lowered to atmospheric conditions, and the production of gas was observed over time. The red line here is the pressure. You can really see it's just drawn down to atmospheric. Now, in the second experiment, we went through a stage-wise decrease of the of the downstream pressure, and we see production following the drawdown, and we end up at atmospheric conditions. Now, so what we can do now is we can say, well, okay, fine. We need to first interpret the loading experiments, and then we want to try to predict the production. Let's see what happened. So we had helium behavior, helium parameters from before, and we would have to rescale our transport now from helium to methane instead of helium to argon. But the Kf value and the ratio of pore spaces in the pore volumes in the matrix remained constant. We went through the same exercise as before by defining the flux as transitional flow, and came up with an estimate of the ratio of these characteristic times as we saw before. This we then use in this table. Now I keep Kf and I keep the volume ratio, but I've rescaled the parameters here. Now, one parameter that we didn't measure, we didn't get kinetic data for methane, because the isotherm was measured in a slightly different way in terms of the data collection. So we didn't have the transition captured between the isotherm points in a good way. So what we had to do was estimate the kinetic constant for adsorption from one loading experiment as a single parameter estimation here. And we use that then to predict the behavior of the second experiment, and things seem to agree fairly well. So we have one parameter that we estimated for methane. And now we have all we need, supposedly, to predict the behavior of the production side. So let's see what happens. Well, on the figure, we see that the model overestimates the overall or cumulative production or the gas recovery at the end of the depletion experiments. Okay? I've listed here the radial gas in place for experiment A and B as calculated from porosity and pressure information, including sorption. So what we see is we have about 9,000 cc of gas originally in place, most of it stored as adsorbate phase. About 2/3 of the gas is stored as adsorbed gas, while only 1/3 as free gas. Same for experiment B. We have slightly more gas in B than in A from our calculations. Now, the production that we calculate is overestimated substantially for both experiments, about 8 to 11%, depending on which one it is that you want. And that sort of indicates this need to include an idea of a residual gas at the end of the depletion experiment. Simply not all gas is produced. Okay? So that is the same as talking about sorption hysteresis. Now, in a recent study that we did, a student measured argon adsorption and desorption on a shale sample from the same formation nearby the samples that we were working with, and observed that the desorption branch departs from the adsorption branch, and that after evacuating for an extended period of time, a little cube sample, he wasn't able to get all the gas out. Okay? And here to the tune of 0.01 moles per kilogram, but you can see it's a good portion of the overall that you don't get back out again. Now, and this is what we believe is also happening during the methane process, that we see here the model that doesn't know anything about hysteresis assumes that all the gas is going to come out, but the experiment says, no, that's not happening. Okay? So what we did was to say, okay, fine, let's come up with a simple way of representing hysteresis. And we used a shift in the desorption pressure. According to this, if you use P prime in your adsorption model instead of P itself, you can introduce a lag in the desorption relative to the adsorption curve. Okay? So there's a parameter, dimensions parameter here, delta, that you need to estimate to characterize the desorption, the hysteresis that you have between adsorption and desorption. Pmax here is the maximum pressure before reversal of the process from adsorption to desorption, and then you basically offset your pressure with respect to that to delay the desorption process. So how can we use that? Well, okay, we have two production experiments. We have our first experiment where we just deplete straight to atmospheric conditions, and we use that to estimate this sorption hysteresis parameter delta, and we end up with sorption curves that looks like this. And then we can use that to predict the behavior of our stage-wise production process. And we observe that we actually achieve a fairly good agreement over the entire range of the depletion process altogether. So we were pretty happy with that, and we see that by shifting the curve over, you end up with a non-zero adsorbed amount after you return back down along your desorption path. So a relatively simple hysteresis model can help us understand this. But again, if we didn't know, we would overestimate our production from this particular chip. And here we're basically just summing up the calculation. We had the experimental observations, the gas recovery from the two different depletion experiments range between, let's say, 75 and 80%, which is fairly high, but you still leave a substantial amount of gas behind. Okay? Now, if we model this without hysteresis, we grossly overestimate the production. Here, to the tune of 10, well, that was 8 and 11% basically overestimation of recovery. But if we include our little simple-minded hysteresis model, we can bring it back much closer to the experimental observations, and we were kind of happy with that simple adjustment of the modeling efforts. So, methane ethane. We're not done with this yet, but we're just working on interpreting these experiments, because now if we load up a mixture of methane and ethane on these samples, we will have to describe competitive sorption phenomena and also the kinetics or hysteresis associated with desorption in these type of processes. We've done some preliminary experiments. In particular, of interest is if we look at the production pressure, which is shown here in stages during a depletion process, we used a residual gas analyzer, which is basically a tiny mass spectrometer at the outlet to monitor the ethane concentration over time. And what we see is a behavior that does not really reflect the concentrations that we would expect, because we loaded up the sample with 10% of ethane and 90% of methane. But during no period of time during our production are we able to reach 10% ethane concentration, even though we pull our pressure down all the way to atmospheric conditions. So there's some indication of substantial hysteresis also for the stronger sorbing component, which is ethane in this particular case, over that of methane. We published the data for mixture sorption as well, alongside the pure isotherms in the past, but we're still working on trying to interpret and make sense out of this type of behaviors when we start looking at gas mixtures being produced from shale samples. Okay. So, without running too much over time, let me sum things up. So, one of the things that I showed you today was that the excess sorption data that we measure for pure substances can be modeled accurately using very different absolute phase density models. Okay? And that suggests that the selected density model can have a substantial impact on gas in place estimation if we use these type of approaches to back out how much gas in place do we have. Another thing we saw was that if we use Langmuir parameters that we obtain from isotherms, so the equilibrium constant and the maximum sorption capacity, if we use that and try to estimate kinetics, we may not be as well off as if we include isotherm parameters alongside the kinetic constants in that process. Because again, we are slaves to the density model that we choose, and our results will be strongly affected by that. Okay? We saw that we could use helium expansion experiments to characterize mass transfer and fracture surface areas from these sensor functions for the full diameter core, which is very helpful. And we could use adsorption kinetics from a cube sample combined with our larger scale measurements with helium to provide a reasonable estimate of argon behavior when it was allowed to expand into the full diameter core. Now, we also work with methane, and we showed that we could use methane loading experiments combined with helium characterization experiments to model the behavior of loading of methane into the full core sample that we worked with. We observed when we produced the gas back that approximately 20% of the gas in place does not come out at the end of production, even though we let the pressure at the downstream go to atmospheric for an extended period of time. And we contribute that to hysteresis during the sorption process. Okay? And we came up with a very simple-minded approach for describing hysteresis, and by introducing this lag in the bulk phase pressure during the desorption process. And we could estimate the lag parameter from one experiment and used it successfully to predict the behavior of the other experiment. So to sort of reach a couple of conclusions, well, sorption behaviors from small scale samples can be combined with larger scale measurements to provide for reasonable accurate prediction of coupled behaviors of mass transfer and sorption. Okay? We also sort of infer that the sorption measurements we do are in the absence of no net stress. And we can even use that to predict the sorption behavior in a larger sample that is under some net stress, which is good. So we don't have to worry too much about the stress state when it comes to the sorption behavior. But it can substantially impact, of course, the transport if we manage to compact things during a depletion process. Now, we saw that absorbing gases are likely to be trapped, and we need to include hysteresis models in our description to get the right recovery amounts and also the right timing of a certain level of recovery. And to do this, we worked around this with a triple porosity model that is relatively simple, but provides enough flexibility to integrate measurements of absorption from smaller scale to mass transfer and sorption at larger scale without needing to discretize everything and know the actual location of fraction networks, etc. What is next? Well, the top of my wish list is somebody comes up with a way of figuring out what the adequate phase density is. And people are getting better and better at molecular dynamics simulation to try to understand these things. The key challenge remains, though, that the materials that we're working with are made up by nature over time and are not nice and homogeneous materials when it comes to surface chemistry. So when it comes to understanding adequate phase density, there's still a lot of work to be done. And while many molecular dynamics people like to have relatively simple structures, that definitely has to be extended to more heterogeneous structures to try to understand and develop adequate phase density models for continued scale observation. Okay. Effects of geomechanics and transport. Well, in our work that I presented today, we didn't really have to integrate it because we observed that the main impact on the fracture perm was not overly affected by in the pressure range that we were operating. This may not be the case for all settings. So, experiments to try to figure this out, particularly stress and mass transfer in the matrix segments could be devised and help to see if that's something that we need to pay special attention to about. Again, just saying that we need to come up with smart sequences of experiments and modeling that allow us to isolate and probe the different mechanisms that are at play. Okay? And then the next thing we're going to hopefully look at is to get into the mixture behavior, try to interpret. We have to extend our modeling efforts to interpret the methane ethane production behavior that we observe from the experiments that we have, and try to come up with nice, ways of interpreting the state of affairs during production as a function of the methane ethane ratio that we observe over time. And with that, I want to thank some of the students that have been part of working with this, particularly to Yuang Desani and Yilu, who's been instrumental in both the experimental work and modeling, and the sponsors of this research. Finally, a shout out for the Department of Energy, and then I'll be happy to take any questions that you have.
Thank you, Kristian. Thank you for sharing your most recent results. And so it's very good combination of experimental and modeling work. And I know that you did a lot of simulation in the past, and so simply recently, and you are more active and in experimental and modeling. So we already got a lot of questions in chat. Professor Yao, so should I read out the question in chat?
Yes, you can do it that way.
Okay.
Yeah, no problem.
Okay, thank you. So we have a number of questions, and just for the audience, if you have more questions, and just ask your question in chat. And I think Professor Yao also will have to transfer the questions from other platform and to Zoom. The first question in chat is, Kristian, you mentioned the first and second approach in sorption kinetics, and what do you mean by those two approaches?
Okay. Let me show you that one here. Where are we at? Here we are. Okay. So when we look at the kinetics of the dynamics of the adsorption process here, we interpret it by a simple-minded Langmuir type model for adsorption, where basically the net rate of adsorption, okay, which is a balance between the adsorption and the desorption. We have to know something. We need to know pKa. We need to know the maximum sorption capacity, and we need to know the equilibrium constant from the Langmuir isotherm. So the Langmuir isotherm uses Nmax here and Ka. That's for the isotherm itself. Then you need to have one of the kinetic constants, because the equilibrium constant in Langmuir's model, isotherm model, is the ratio of the kinetic rate for adsorption over that to desorption. Okay. Now, when I interpret this data, I can do two ways. I already have the isotherm here. I can get my data, I choose an adsorbate phase density, and I interpret the equilibrium data points, and I can get Ka and max according to the Langmuir isotherm that we have here. Okay. Now, and then I can go in and say, well, now I just need to estimate pKa. So in the first approach, I fix Ka and the max adsorption amount based on what I have at equilibrium. Okay. And then I estimate the value of the forward constant where we adsorb things onto the surfaces of the shale sample. So, and in the second one, I said, well, look, I can also estimate all three parameters at the same time. Okay. And it turns out that you get a better handle on the observed transient in terms of the excess adsorption if you do that. And the reason for it is that whenever we convert excess adsorption data to absolute adsorption that we need for the Langmuir model, we make this assumption about the adsorbate phase density. Okay. For instance, I assume that the adsorbate phase density is constant. That would mean all the way along this process, the adsorbate phase would be the same, regardless of how much I have adsorbed onto the surfaces. Okay, and that may not necessarily be true. So the model that is written here is one that attempts to change the adsorbate phase density as a function of the fractional coverage. How much gas have I stuck onto the surface will dictate the density. Okay. Now, but there's no guarantee that this is the exact model of what the adsorbate phase density truly is. So whenever we play this trick of converting from excess to absolute to learn something about rates, we fold in our assumption about the density that may be good or bad. And that reflects then into the value that you have for Ka in abs and your adsorption constant. I'm sorry, your adsorption rate constant, Ka multiplied by B here. And in the other approach, if we sort of relax that idea, and you know what, I know that I'm not very good at estimating adsorbate phase density, so I'm going to estimate all three at the same time. I get a far better agreement in terms of the root mean square error between model and data. So that's the second approach. And it's one parameter versus three parameters that you estimate. Okay.
Okay.
I hope that answers that one.
Yeah, thank you for the explanation. The second question is, I think maybe you, you mentioned that. So, do you assume the properties of the matter constant or variant with conditions? I think that you. I think, as I understand, you assume that fracture permeability will change with the stress. But do you assume other constants, other parameters are just constant, or
a function of stress? So the only parameter that we have information about this direct impact of stress change is the fracture permeability that runs down through the system. Okay. The other parameters, we don't have ways of measuring directly what is, for instance, the impact of, let's say, just the characteristic time for mass transfer in the matrix as a function of net stress. For me to do that, I would have to do experiments that directly measure the, let's say, the diffusivity of gas through the matrix segment in the absence of the fracture. And then, and we haven't done those type of experiments because that would require you to take out a, let's say, a pristine subvolume of matrix without any micro cracks or fractures inside, right? And try to do mass transfer experiments into those. So it's really hard to at least in my mind, and there might be some good solutions out there that I'm unaware of, where to integrate the impact of net stress on, say, mass transport in the matrix. Also, what about adsorption? Will you have an impact on stress on the adsorbed amount? And that is also something that is not trivial to measure in my mind, at least. I think it's really difficult to separate it out. Because the shales that we are working with are very heterogeneous materials and oftentimes have some, microfracture or cracks embedded inside that we are not able to separate out from the observations that happen.
Yes.
So the short answer, we only considered that stress on the macro fracture permeability in the system.
Yes. So I think that's something that you can get from experimental measurement, and you do realize that maybe other properties may change with the stress. But
yes, so some of them may, but we haven't gone after trying to measure any of them explicitly yet. And one of the reasons was that the student who did all the good work graduated. That's one thing that always happens. And also we didn't seem to be needing additional parameters to capture the large core experiment where we had pressures varying from, net stress varied 1,000 psi, and it didn't seem to be important to include a net stress effect for us to be able to capture the data or to model the data. And that was also, I must admit, I was surprised that it didn't matter more. But the core tells the story, and we just try to model the story that we observe, right? So
yes,
that's how it goes.
Okay, thank you. And the next question is about slide 37.
Right.
It's about the hysteresis. So you got the results.
Here.
30, yeah, I think, or maybe then it's not 37, maybe 35. Yes. So the results of with hysteresis is better than those without it.
Yes. So for us, I mean, for the, if I back up to the experiment here, where we just try to predict the behavior without adjusting any parameters here, right? We learned something about the adsorption rate from the loading experiment, and now we're just letting gas be produced out of the system. And the model doesn't know anything, doesn't know any difference between loading and unloading. And that's where we saw this big gap between model and experiment. And then it turns out that this can comfortably be explained by looking at sorption hysteresis in adsorption versus desorption, between resorption and desorption. And the key thing here is the difference at low pressure that you observe between loading up gas on the sample and taking it out again. You end up with a gap, which is caused by, which is hysteresis that we observe this way. And this difference will basically tell you that some of the gas that you put in is not going to come out. All right. And that's exactly what we observe here. The only problem is that the model doesn't know it yet. We have to tell the model that some of the gas that we put in will not be able to get back out. Okay. And once we include this gap here by our little simple-minded model, we can estimate the parameter that describes how much will not come out from one experiment. So that's why it's, I mean, there's a good reason why this is a good agreement, because we estimated a parameter extra here, right? But the good news is that when we use it to predict the other one, it greatly improves the agreement between the model and the experimental observation. So that's why it works better.
Yes. So
I believe that it captures some of the stuff that's going on because we have seen it in separate measurements, yes. And this is just one way of trying to integrate that in the model. Right?
Yeah, I'm not sure if I understand correctly, and so it seems that in this case you need to measure both adsorption and desorption for methane. So to have this experimental information, and then then you can predict.
Yes, then you could. But again, I think so. The student did it. This is for argon, unfortunately, and we haven't done production for argon. So we never actually needed this. It was the first time we did the production was with methane, because for argon we had only done loading. But she was curious about it, and we realized, oops, there's something going on here. Now, the mechanism behind this is something that I do not fully understand. That she did this. This is for a 1 centimeter cube sample. That she had sitting in this magnetic suspension balance under vacuum for multiple days, and the mass did not come back down again. She couldn't recover back to the original state. The molecules got stuck in there somewhere and did not want to come out. So
yes.
So that's sort of, if anybody can explain to me why the gas doesn't want to come back out, I'll be happy to know. If they have any good explanations for that.
Yes. So okay. My understanding was wrong. So this methane adsorption desorption is modeling results based on argon. It's not this miss. Yeah, right.
So this curve here, this is not a measurement. This is
a model.
This is basically when we estimate delta from the first production experiment. It translates into a relationship between adsorption and desorption that looks like this.
Yes. Yes.
Calculated, right?
Yes.
And that's, then when we predict the second one, things look much better than without it here.
Yes.
Okay.
So that's a question in this. Sorry. Yeah.
No, go ahead.
A question in this connection is that I'm not sure if for helium you have this kind of. I know that usually we assume that it's not adsorption for helium, but for helium, can you see any hysteresis effect?
So okay, so helium is a tricky thing, and we have a paper out that came out last year where we basically demonstrated that helium is not completely inert. And one has to be a little careful when particularly if you try to interpret dynamic data during the adsorption process, you have to be a little careful. And there's a lot of people are working with this type of magnetic suspension balance to study adsorption behaviors. And if you have materials with very low sorption capacity, one has to be careful because the helium calibration assumes that there is no adsorption, but there is a tiny amount. Okay. Yeah. And if your sample, whatever gas that you're interested in, also has a very low sorption amount, it can cause some problems. I'll be able to share that reference because it's actually an interesting thing to see. You can show that helium is not completely innocent. Okay. It's a troublemaker too.
Yeah. Okay, I think we have one more question in chat, Professor Yao. I'm not sure if there are more questions in other platform. If there are any, and just let me know. And the question in chat, the last one is about the mixed gas. I'm not sure if I understand the question completely. What is a mixing method to get the pressure?
Well, I didn't spend much time on this particular one. I can mention that we did the same type of sequence of experiments where we took the whole core system and we saturated it with a mixture of methane and ethane, where it was 90-10 mix. Okay, and we loaded it up to 1,000 psi, and then started this depletion process in pressure stages. This is us controlling the pressure. Okay, and then the ethane concentration in the effluent is shown here as the gray line. Okay, the interesting thing for us to observe here was that, well, we put 10% in, but we get substantially less out in the production stream. Okay. So the original, let's say, gas in place is not going to be easy to estimate from the production figure like this. What we do see is that as we decrease the pressure, okay, fine, ethane goes down, more and more methane comes out. But then at the end, when we drop the pressure to atmospheric conditions, ethane concentration increases, which suggests that the process of the desorption is gonna be a little more difficult to interpret than just that of a pure substance in place. And we're still working on extending our modeling to try to describe this process in our triple porosity model that we've been working with. But it's not a straightforward extension, but work in progress. Next time.
Yeah, it's challenging, and also I guess that the composition also vary with time, or depending on the desorption process.
Yeah, the desorption process, and when you have methane and ethane competing over sites forced to be adsorbed in, the desorption process becomes even more complicated than the hysteretic behavior we saw for pure gas like methane. I haven't seen many studies on sorption hysteresis when it comes to gas mixtures. I've seen several studies for pure species on coal and on shale, but I'm not sure that sorption hysteresis for gas mixtures is well understood. At least I do not understand it yet. I'm not afraid of admitting that, but if somebody knows a good way of doing that, please let me know, because then I can model these experiments faster.
Yes. I don't see more questions in chat. I have one question. Actually, we are very close to time. And
okay.
One question about the simulation side. And I know that you have you proposed this triple porosity model, and it seems to be quite successful, and to upscale and from your very small cubic centimeter experiment and to the full diameter core scale experiment. But of course, that for the production, you need to predict the behavior on the even
you need to go much larger than that.
So just can you give some perspective on that, and what is your plan, and how do you want to model that process?
So I think my thinking is we haven't tested the idea yet, but if I back up to the model here, well, we're working with these characteristic times, okay, and effectively it's a characteristic time for a certain volume of your shale that you're looking at, okay, and because let's say the shape factor, which is surface area per volume and characteristic length, that's really what it is, a shape factor, okay, and an effective diffusivity. So the question is, which one changes? I change the length scale of the sample, and this guy here will change, and the question is how the surface area will go with it, because if you have a very, let's say, uniform fraction network in your system, or uniform characteristics in your matrix, then it's not difficult to scale this up from lab to larger scale. The problem is if you have a very heterogeneous setting with, well, some regions you have high intensity of cracks and fractures, and others less so, which is probably what you will find in a shale gas well, right? That you've stimulated close to the stimulations, you have a lot of fractures, and then the further you go away, the worse it gets, right? In terms of that. But I think that working with the concept and the ideas of characteristic time for mass transfer at different scales is a path to go forward, rather than trying to describe all the physics that's going on, because it's simply impossible. That's my thinking, that if we can build models that acknowledges that different scales at which things are occurring, and each of them is associated with a characteristic time, then we can try to estimate those characteristic times from production data, and then use that for history match. It's going to be a history matching exercise one way or the other, because we don't have all the information we need. We never do. But at least we can use the laboratory scale to sort of inform us in setting up things that might work at larger scale. And then you test it out.
Yeah. But do you suggest using this triple porosity model and for large scale simulation, or?
Well, I mean, if you can get away with it, sure. So, but I'm not sure it's feasible, because at some point, if you start building large reservoir or large well models, for instance, and you subdivide things into into your simulation mesh, you would have for each of those have to assign some sort of characteristic time for your hierarchy of transport processes. You know, fracture to meso, meso to micro, and that's it. But it may not be impossible to do. But I'm not sure. I don't have the recipe for how to take this directly to larger scale. But we're still thinking about it. We still have. I'm not retiring until 2030 plus. That's a good news. All right.
Okay, thank you, Kristian. I don't see more questions and in chat. And Professor Yao, do we have more questions? And
Okay. Thanks a lot for Jessen's excellent presentation. Thanks, Professor Jens, hold this meeting. You know, the time actually is limited. And Jessen, there is a deadline already. Yeah.
It's
so I'm
getting
thinking,
close. It's getting close. It's bedtime.
yeah. So I'm thinking that today is all right, and we will collect the other questions later, and I translate to you by email.
Okay,
And,
that's great.
Yeah, by the end of the meeting, I'd like to give you the information. And today we have other platform. There are more than 3,000 persons leading to your presentations. More than 3,000. Yeah.
Wow. Okay.
Yeah.
Okay.
We have other platforms such as Facebook, and the YouTube, and other Chinese platforms. Yeah. So I'm thinking after today you will be famous in the world.
Well,
Okay.
I hope I didn't say too many silly things then with so many people listening, but that's always good. Thank you very much. Thank you very much for arranging all of this and inviting me to give the talk today.
Yeah.
Great pleasure.
And
thanks.
thank you very much, and have a good night. Yeah.
Thank you.
And
And
thank you.
I'll see you soon.
And
Wait, take care.
see you.
Yeah,
See you in the
see you.
future.
Yeah.
See you. Yeah.
Yes, thank you for everyone. Yeah. So see you.